Welcome to the second lecture on HMMs. We cover forward and Viterbi algorithms in this lecture. Let's look at the parameters or the conditional probability tables for HMMs as a special case of Bayesian networks. Um, Obviously, we should have a conditional probability table for the first state or the initial state denoted by pi of x1. Then we need to have CPTs for generating the observations from the states denoted by O of E given x, and then we need to have transition probabilities for which is denoted by T, probability of the next state given the current state. Simply speaking, the parameters of an HMM are as follows. We have three sets of parameters in our collection. First, the initial state probability, pi of x1, then the transition probabilities, t of x prime given x, the next state given the current state, and observation probabilities, O of e given x, which is the probability of observation e given the state x. Now that we have the parameters of our HMM, let's see how we can write down the joint probability of a sequence of states and observations from those states. The joint probability of n states x1 to xn and n observations from those states e1 to en is written as the probability of the first state pi of x1 times the probability of generating the first observation in the first state O of e1 given x1 times the probability of going to the next state t of xt given xt minus 1 times the probability of generating an observation from the new state p O of et given xt. So we, for each state and observation from time 2 to time n, we multiply these two probabilities. There are two main inference problems in hidden Markov models. First is the filtering problem, which is what's the probability of different states in time t given all of the past observations, or equivalently what's the probability of xt given e1 to et. And the second problem is what's the most likely sequence of states given all of the observations so far, or equivalently we are interested to find the best sequence of states x1 to xt, which maximizes the probability of the sequence of states given all of the past observations e1 to et. Let's first look at the filtering problem. Now let's look to see how we can drive the forward algorithm. We are interested in this quantity p of xt given e1 to et, or equivalently the probability of the last state given all of the observations so far. It can be written as the joint probability of x1, x2 up to xt given e1 to et, where the states from x1 to xt minus 1 are summed out or marginalized out. It's on the basics of probability. Then, based on the independence assumptions encoded in HMM, the probability inside can be decomposed as following: p of et given xt times p of xt given xt minus 1 times p of x1, x2 up to xt minus 1 given e1, e2 up to et minus 1. Okay. Then we can push out the probability of et given xt outside the summations because it doesn't depend on the summations. Similarly, we can push out p of xt given xt minus 1 in front of x summation over xt minus 1 because it is independent of the rest of the summations, and then we leave the rest of the terms. The first term is indeed the probability of the observation et given xt. Then the second term is indeed the transition probability of xt given xt minus 1. And interestingly, the last expression is indeed the probability of xt minus 1 given e1 to et minus 1 based on the basics of probability. To summarize, the probability of xt given e1 to et can be written as the probability of the last observation given the last state, O of et given xt, times a summation over different states in previous time step, or xt minus 1, where in the summation we have the transition probability of going from the state in xt minus 1 to xt times the probability of xt minus 1 given e1 to et minus 1. If we denote p of xt given e1 to et by b of xt, or our belief about different states in for time t, then p of xt minus 1 given e1 to et minus 1 is indeed b of xt minus 1, or equivalently our belief about different states for time t minus 1. This recursive formula suggests a dynamic programming algorithm for computing the belief about different states for a particular time step. Suppose we have the belief for possible states in time t. For example, suppose we have three states, s1, s2, s3, and we have our belief of these states, b of xt. Then to compute the beliefs for possible states in time t plus 1, we do the following. We send messages from states in time t to states in time t plus 1, and then do a summation based on these messages to compute the belief about s1 and then s2 and then s3 in time t plus 1. Now let's look at the most likely sequence of states problem, i.e. the argmax of p of x1 to xt given e1 to et. We want to find the best possible sequence of states which achieves this maximum. The Viterbi algorithm is a dynamic programming algorithm to do this. Let's define some notation. mtx to be the maximum probability of x1 to xt, where the last state xt is fixed to x, and atx to be the best sequence of states which achieves this maximum probability. Then it's obvious that we can read off the best sequence out of m and a vectors. Let's derive the recursive formula which leads to the Viterbi algorithm. The maximum probability x1 to xt given all of the evidences e1 to et, where the maximization is over the states from x1 to xt minus 1, can be written as the observation probability of et given xt times a maximization over xt minus 1, where inside the maximization we have the transition probability of xt given xt minus 1 times the maximum probability of x1 to xt minus 1 given e1 to et minus 1, where the maximization is over x1 to xt minus 2. If we denote the left hand side by mtxt, then it's obvious that the last term is indeed mt minus 1 xt minus 1. By the way, this decomposition or equivalence between the left hand side and the right hand side is derived by some steps similar to what we did for the forward algorithm. So in short, mtxt is proportional to the probability of the last observation given the last state times the max over xt minus 1 where inside the maximization we have the transition probability of going from xt minus 1 to xt times mt minus 1 xt minus 1. We can look at the Viterbi algorithm as a message passing algorithm like what we did for the forward algorithm before. Suppose we have mt for all of the states s1, s2, s3 in time t, and we want to compute mt plus 1 for the states in time t plus 1. We send messages from time t to time t plus 1, and then these messages are combined, but this time based on the maximization operator instead of the operator that we used before in the forward algorithm. That's the end of the mini lecture.